In our previous lectures, we learned that diodes allow current to flow in one direction. And we know that this is a very useful property in many applications, such as AC to DC conversion. And this is known, AC to DC conversion is known to be something called rectification, and the circuit is known to be a rectifier circuit. So you remember very well that when we talk about a circuit where you have a diode, we said like this, we know that this diode will allow the current to flow only in this direction as long as the voltage, which we call it VP, is greater than a certain threshold voltage. And as I just mentioned in a few minutes, that this property will help us in making what we call it rectification or AC to DC conversion. And we will be seeing that the rectification process could be, rectification can be as half wave, could be a half wave rectification, so it's a half wave, or it could be a full wave rectification. In this lecture, we will be concentrating on the half wave rectification, and for sure in our next lecture we will be working on the full wave rectification. So when I said half wave rectification, exactly by that. So let's see a circuit. Here we have a circuit where I have an AC power supply or voltage. So this is my voltage, this is time, and simply I would like to see what will happen in case I have this source or supply is actually, it's an AC alternating, is applied to a circuit where I have a diode and then I have a load. Actually, if you remember in our previous lectures, we used to have, instead of an AC, we used to have it as a DC power supply. And in that case, we said only if this is positive compared to this one, we will have a current flow, and therefore the voltage will be the voltage as this one. So this is exactly the same. And what we are gonna do is to say, okay, if this is the case, then I know that this is the voltage, and in the positive cycle, if I have the positive cycle, in the positive cycle, okay, which is this one, I will be having, assuming that this is an ideal diode for the time being, assume that it's an ideal diode, I know that whenever the voltage is greater than 0, I will be having here a conduction, and therefore the voltage here will be the same as the voltage here. And therefore, I will be able to see that in this case, what I'm gonna have is, this is my output. So this is time, and this is the output voltage, this is V output, and this is my V input. So the output voltage will be the same as long as the voltage at this point, which is the anode, is greater than the value on the cathode. And we said, because it's ideal, we'll assume it to be 0, and that will be the, what we call it, the maximum voltage, which is the voltage here. Let's say that this is Vm sine or cosine omega t. Now, once I have the negative cycle, so for the positive cycle, this is represented as what? As we said, we will be saying that, okay, this is positive, negative, I have here a short circuit, and then I have this, and therefore my voltage here is this one. Now, in case of a negative half cycle, then in that case, what I'm gonna have the following. In the negative half cycle, that will be like negative positive, and this is my diode, and then it will be represented as what? As an open circuit, because simply the voltage here is less than the voltage here, and therefore what we will be having here, we will be having a 0 output. So this is the full period T, this is T over 2. So if this is So I'm talking about here that this is T over 2 and this is the period T. So in the positive cycle I have this one, in the negative cycle I have a zero output voltage. So if you can see by doing this, what we are having, if we continue for the next half of the cycle, which means that if I would like to continue showing you the output, it will look like this. If this is my input, and I would like to show you the output on the same graph, so this is V input and this is T, then the output for a half-wave rectifier will look like this. Okay, I will be having this one, sorry. Here we'll have this, and so on. So that will be the first one, then 0, and the second one, then 0, and so on. So as you can see, this is my output voltage, and this is time, and you can see this is what? This is a pulsating DC signal. So this is an AC signal, and this is pulsating DC signal. And as such, we are doing what we call it half-wave rectification. Now, simply, we need to do just some calculations or some values. In practice, first of all, we'd like to say that this is not exactly the way it should be, which means that I know that in practice, the voltage for the diode will not be conducting unless the voltage is greater than 0.7. And therefore, if you need a real practical case for the output voltage, it will look like something like this here. It will look like this, and then the same thing, and then here the same, and the same, and the same, and so on. So practically, or in practice, we expect a little bit of variation, but we may just ignore it because it's not that much as compared to the voltage that we will be having. And not only that, we will be seeing that in practice, the output voltage here, the peak here, it will not be equal to Vm. It will be Vm minus 0.7 volts. But generally speaking, Vm is very high compared to this 0.7, and therefore we will be neglecting the drop, and always we will just assume that we have the Vm voltage. Now, there are some parameters that should be, or that are directly associated with half-wave rectification. The first one is called the average value. So if I would like to start with the parameters associated with half-wave rectification. As I said, the first one is, let me just write, first one is the average value. So what is the average value? As we said, if that was my original signal, which is the AC power supply, we said this is T over 2 and this is T, and we mentioned that our output will be only like this. So from the mathematical, so this is V input, this is V output, and this is Vm. Of course, this is the same Vm. Now, this is T over 2 and this is T. As we know from mathematics, we don't have to read it here, that the average value, V average, of any signal can be represented as 1 over T, which is the period integration from 0 to the period of the function V of T dt. Now in your case here, you can represent this as you know as what? Here, this one from time equals to 0 less than T over 2. This can be represented as what? As Vm sine omega T. And it will be 0 for this one, so it will be for T greater than T over 2, less than T it's equal to 0. So all what you need is just to substitute, and that will be straightforward. It will be 1 over t integration from 0 to t, the function which is Vm sine omega t dt. If you execute this one, of course, plus 0 for the other one because this is 0. If you do that, you will find that your average value, and this is all what I need from you to know, that the average value for a half-wave rectifier is nothing but the maximum value divided by pi. That's it. You don't need to know anything else. That's all what I need you to know. The next parameter we have to talk about is called the RMS value. So the second parameter is the root mean square value, the RMS value. Okay, I'm sure that you were exposed to this one before. And again, the definition from it is root mean square. So the function will be squared. So the function v of t will be squared dt, and then the root mean square. So this is the mean and this is the root. So root mean square of the function. And if you do that, you don't have to do it here again. It's nothing but the maximum value, it's the maximum value divided by 2. So it's the maximum value divided by 2. So for half-wave rectification, we need to know those two parameters very well. The average value is equal to the maximum value over pi. The RMS value is the maximum value divided by what? By 2. And therefore, I can even calculate what will be the average current in case of half-wave rectification, because I know that the average current will be equal what? Simply, it's nothing but the voltage, because it's the same. It's the voltage divided by what? It's the voltage, which is the average voltage divided by the resistance RL. And we know the average voltage we just calculated here in the previous part is Vm over pi. So it will be nothing but Vm over pi RL. So it's nothing but just application of the Ohm's law. And then we have one more parameter. It's called the peak inverse voltage. So the third one is called peak inverse voltage. And again, this is given that PIV. And this is nothing but the maximum reverse voltage which appears across the diode during a certain operation. Simply, if I have my diode like this, but I know that the voltage is in the opposite direction, this means that there will be a certain voltage that will appear across this diode in the case of operation, which is the maximum, reverse voltage. And in this case, it will be, as an example for me, it's Vm, because I know that the voltage here is Vm sine omega t. So the maximum in the positive will be Vm, in the negative, which I care about very much, will be again Vm, and this will appear when the diode is in the reverse bias direction. Maybe the last one, actually, or the one before the last one, is called the ripple factor. And this is called ripple factor. Again, this is due to the fact that, as you noticed, our output voltage of the rectifier is not pure DC. We said we are converting from AC to DC. So the voltage as we have, we said it looks like this, and then so what does that mean? That means that we have some ripples, which means the voltage will go up and down and up and down and so on. So this is called the ripple factor. This ripple factor is usually so important that we would like to minimize it as much as possible. Would like to have one way of reducing this ripple factor is by using a capacitor, as I will show in the next figure. So here, what I will do, I will just have my AC power supply, and this is our diode, and this is our original case where we have this circuit is coming, or this output is due to this circuit. Now we can do one more thing. We can add a capacitor in this circuit here to the output. This is RL and this is a capacitor C. Now notice what will happen. What's gonna happen is the following. The minute I have the voltage greater than the threshold here for the positive half cycle, I will be having the diode as a short circuit, and therefore the voltage here starts building up. So my capacitor will start building, okay, as we said. So the voltage should be like this as the original case, and like this, but with the presence of the capacitor, look at what will happen. The minute the voltage or the for the half cycle, the positive half cycle, the capacitor is charged until the voltage reaches the maximum here, the max. So the capacitor starts charging while this is on, start charging until it reaches a maximum value here, and once it reaches a maximum value, the voltage across the diode becomes between this point and this point equals. So if I have Vm here, the voltage will be here Vm. So if this is Vm and this is Vm, the diode is not anymore conducting. It's not anymore a switch which is closed. It will be an open switch because the voltage is less than the threshold. And in that case, what happened is that we can say that this portion or this part of the circuit now is open, and the current now, or the capacitor, starts discharging through this resistance, and therefore here I will be having some discharge of the capacitor. So the voltage will look like this as an output voltage. So it will build up to this point and then discharges again. Once it reaches this value, again this will be less than this voltage and the capacitor charges again. So I will have this one going on again this way until it reaches the maximum value, and then again this diode is not anymore a short switch, it will be open, and again the capacitor will start again discharging, and the process continues more and more. And in this case, definitely we are improving a little bit the shape of my waveform. The output voltage will be much better. The most important thing in order to get good shaping here for the charging and discharging of the capacitor is to make sure that the time constant RC of the RC circuit is much greater than the time, the period of my power supply, which is the time t. The last thing that we do have is what we call it the efficiency of my rectifier circuit. So the fourth one or the fifth one is called the efficiency, and we know that the efficiency in this case we mean by it, and usually it's given the ETA symbol. It's the DC power or output power, let me say DC output power. Okay, so it's a DC output power over the AC input power. Of course, we like to have it as high as possible, but unfortunately, for the case of half wave rectifier, this is equal to 40.6%. We don't have to prove it for you, but it has been found and proved mathematically that it's not more than 40.6%, which is quite low value. This is why we would like in our next videos to talk about the full wave rectification. Yes, it's more costly, but definitely the efficiency will be more and more. So the application of this half wave rectifier could be in many, real life applications. Looks like the following. I mean, as an application, I could have, as an example, a power supply connected to a transformer, which is called step down transformer. And then this step down transformer is connected to a half wave rectifier, and then the output that we just show in the previous slide will be filtered using some filters, and one of the filters is this C capacitor that we just put, so a filter. And then after filtration we may need still to do some kind of regulation, so we may just connect it to a regulator, and then finally it is connected to your load, whatever it is. So this is your load. Now let's have just very simple examples to demonstrate what we did. Simple examples. First example is the following. Assume I have a circuit like this where I have the voltage is 5 volts and it's connected to a diode, okay, and this diode is connected to a certain load. So this is RL is equal to 1 kilo ohm, and assume that of course this is a silicon diode, and the diode would like to try to solve the problem by calculating what is the output voltage, what will be the output, which is here, in case we include or exclude the threshold of the diode. And that's so simple. We said that in this case we know that the output voltage, or the output actually peak voltage, will be nothing but what, in this case, if I just exclude the threshold, my output will be simply like this. This is my output if I exclude the threshold. So simply that will be your 5 volts, and then here you have 0. And if you include the threshold, it will look like the same, but this will be 5 minus 0.7, which is 4.3 volts. Now, if I ask you, okay, this is your peak voltage, how about your let's say average value? We said we will have an average value that is what? That is this value, which is V, in this case output, whatever it is, it's either 5, it's Vm, or Vm minus 0.7, and then that will be divided by 5. This is for this. This is what we, so the value will be, let's say for this case, it will be the V average is 5 over pi, and that will be 1.591 volts, and for this case the average value will be 5 minus 0.7 divided by pi, and that will be 1.36 volts, definitely less than the other one. And of course we can, if you wish, calculate what is the RMS value for each one. The RMS value for both of them here, RMS will be VRMS will be again 5 divided by 2, and for this one, the RMS is equal to 4.3 divided by 2, and we said if we would like to calculate the current, we could calculate it just dividing this this value divided by the average current will be this value divided by RL, which is 1 kilo, and the same thing for this one.